Polygons are 2D plane figures that have certain characteristics. Polygons, first of all, we classify them based on the number of sides that they have. So a polygon with 3 sides is known as a triangle, 4 sides is known as a quadrilateral, 5 pentagons, 6 is a hexagon, 7 is a heptagon, 8 sides is an octagon, 9 sides is a nonagon, 10 is decagon, 12 dodecagon, and an n, a polygon with any number of sides represented by the variable n, we call it an n-gon. So a polygon with 21 sides will be a 21-gon. Okay, so what makes a 2D figure a polygon? There's certain characteristics that all polygons have in common. The first is that polygons are all composed of segments. So we talked about segments in a previous video. Segments by definition are straight because they're parts of a line. So there can be no curves in a polygon. If a 2D figure has a curve in it, then it is not considered to be a polygon. So something like this is not considered to be a polygon, right, because of this curve. So polygons by definition are composed only of segments, and segments by definition are all straight. The polygon has the sides of, or the segments that compose a polygon are called sides. So for a triangle has 3 sides. That means it has 3 segments. And for each of those sides, each side of a polygon meets exactly 2 other sides, and only 2 other sides. So for example, if you look at this side here of the polygon, it meets another side here at this vertex, and it meets a second side here, and no more than that. Okay, and likewise, this side meets another side here, and it meets another side here. Okay, and then likewise for the third one. So for any polygon, it can only have a situation where each vertices meets exactly 2 other sides. So an example of a figure that is not a polygon is if we have something like this. Okay, this is not a polygon because if we look at, say, for example, this side here, this side meets another side here, but then it meets 3 other sides right here, 1, 2, 3. So this one side meets 4 other sides. So therefore, this is not a polygon. So this is not a polygon, and this is not a polygon. All right. And because of that, each side can only meet 2 other sides, another example of something that can never be a polygon is something like this. So if we have a figure that looks something like this, okay, so we typically will say that polygons have to be closed, but really that's just restating this same rule about the sides, right? Because if we look at this polygon, we can see it doesn't follow that rule because this side here, it only meets with 1 other side. It does not meet with the required 2 sides to make it a polygon. So essentially, if you have a figure that is open, that is not closed like this, then it is not a polygon. One special type of polygon that we're particularly interested in is something that's known as a regular polygon. Okay, it's known as a regular polygon. And a regular polygon is a type of polygon. It fits all the rules of a polygon, but in addition, it is equiangular and it is equilateral. All right. So a regular polygon is equiangular. And it is equilateral. So equiangular means that all of the interior angles of the polygon are equivalent. So in the case of this regular hexagon, we see here that if this one angle is given as 120 degrees, then all 6 of these interior angles, which are obtuse angles, all 6 of these angles are 120 degrees. That's what equiangular means. It means that all the angles are equal. All the interior angles are equal. And a regular polygon is also equilateral. This means that all of the sides are equal in length. And so in geometry, we have this single tick mark here that we measure, the single tick mark that bisects a segment is how we indicate that the segments are equal in length. So a regular polygon means that all sides are equal and all the interior angles are equal. Okay, so this is why this is a regular hexagon. And finally, we can classify polygons as being convex or as being concave. Okay, a convex polygon, like the orange pentagon shown here, has a situation where all of the vertices of the polygon are essentially pointing, if you will, away from the center of the polygon. So this is the center of my polygon. Notice that this vertex here is making an arrow almost, and it's pointing away from the center of the polygon. Okay, so anytime we have the vertices, all of the vertices pointing away from the center of the polygon, then we know that we have a convex polygon. Another way we can also look at that is that if we were to attempt to draw a curve around the outside of the polygon that intersects, that goes through all of the vertices, we can do that without crossing any of the sides. All right, we don't have to cross over inside of the polygon in order to draw a curve that crosses through all of the vertices. We can contrast that with a concave polygon, which part of it seems to cave in on itself. So here we can imagine that this particular vertex is actually pointing in towards the center instead of pointing out. So all the other ones are pointing out, but we have one vertex that is pointing in towards the center of this polygon. So this is a concave polygon. And similarly, a test we can do for concavity is that if we attempt to draw a curve that intersects each of the vertices of the polygon, we cannot do that unless we cross inside of the polygon, unless we cross into the interior of the polygon. So this vertex here, the one that is pointing inwards towards the center, we can't cross that with a curve unless we were to take that curve and go inside of the polygon and cross over the sides, okay? So convex, all the vertices are pointing out. Concave has one of the vertices that is pointing in toward the center of the polygon.